Welcome to module number 3 of 4.6 related rates. This module is going to focus on similarity and proportion problems, which sometimes get confused for Pythagorean theorem problems since it might involve a right triangle, or oftentimes get confused for geometric formulas because a lot of times they involve geometric shapes. What these types of problems have that other problems don't have is these problems will describe a situation in which there will be similar triangles or similar cones. And whenever you're dealing with similarity in geometry, that means there's always a proportion that can be set up based on how the two shapes relate to each other. So the main skill that you have to have in this module is being able to see similar shapes and set up the proportions based on those shapes. So let's take a look at our first diagram here, which is a picture of two similar triangles. Now, the main thing that you have to know how to do when dealing with similarity is really just be able to see the two triangles clearly. So if this is helpful for you, I'm going to outline this first triangle here, the smaller one in blue, and then I'm going to outline the bigger triangle here in red, the one that encompasses the blue triangle as well. So when dealing with a problem like this, it's helpful to draw these two triangles separately. So the first one, the blue one, is pretty easy to draw, but to label this one, again, all you need to do is take a look at the diagram and notice that it's 5 over there on that side and then an S over here on the bottom. Sorry, by the way, 5s and S's look really similar. So for the blue triangle, that one's pretty straightforward. Now for the red one, the bigger triangle, on the left side, that's pretty obvious, that's a 20, but on the bottom side, if you notice, that distance called X is going to be added to the previous side, which was S, and that represents the bottom side of the bigger triangle. So sometimes you have to think a little bit specifically to get these diagrams labeled this way, but once you do, here's how easy it is to set up the proportion. A proportion is merely just two equal fractions. And so, to be honest, how you choose to set this up is up to you. Some people will stick to the small triangle here, 5 over S, so that is like saying 5 is to S as 20 is to X plus S. And if you notice, just keeping the blue information on the left, red information on the right, shows the consistency and sets this up the right way. Now what's cool is some people actually prefer to set this up differently. And instead of relating one side of a triangle to another side of the triangle, instead some people will say this: 5 is to 20 as S is to X plus S. So if you notice, it is a slightly different way of approaching it, but the beautiful thing about proportions is that either way you set it up, if you notice I kept the blue stuff over here on the left, the red stuff over here on the right. In this other situation, I put the blue stuff on top, the red stuff on bottom. The beauty about proportions is that when you go to solve a proportion, the skill or the technique is just simply cross-multiplying. And if you cross-multiply S times 20, and if you cross-multiply 5 times the quantity X plus S, what's cool is in the other proportion, it's the same thing. 20 gets multiplied by the S, and the 5 gets multiplied by the quantity X plus S. So again, it really doesn't matter which one you chose, they're both good. So what do we do to solve this? Well, choosing either one, you cross-multiply. So in green, we would have 20 times S, and that would be equal to the purple, which is 5 times quantity X plus S. Now, what do you do with this? Well, you can't actually solve for either variable or solve for a variable, but you can get an equation that shows the relationship between how X and S connect to each other. So in this case here, I'm just going to take 20S and then distribute 5, giving us 5X plus 5S. And I could just real quick subtract 5S from both sides. And once you do that, you're left with this equation here. You get 15S equals 5X. Now, what this really shows you is that X and S are two variables that are connected to each other in this problem. If you change one, then the other one will change according to how the similar triangles work. So if you want to get this equation any more simplified, you could divide by 5, which would give you 3S equals X. So that is a useful equation for us that tells us that technically x is 3 times bigger than s. So s times 3 is equal to x. If you wanted to instead solve for s instead, you could easily get s is equal to 1/3 x if you wanted. And either one of these are helpful for us. You'll see that in similarity problems, once you have this connection, one of these two equations, most of the time the problem will tell you the specific rates needed in order to solve the problem. So that's where we'll conclude this example, or this diagram. And now let's actually take a look over at the other one, which also looks like two similar triangles, but in fact this is going to be something else we see later on. So first off, once again, the main skill is seeing the diagrams, the two similar shapes separately. So here we have a smaller triangle, and surrounding it we have a larger triangle. And again, this is something that's it's helpful to be able to get both diagrams drawn individually and accurately. So here we have the small triangle. This letter right here, R, there is a reason why that's going to be labeled R, you'll see very soon. And then that distance right there is called H for, you probably guessed, height. Now, that's pretty easy to diagram, but take a look at the red triangle, the bigger one. This time there's nothing too weird here, no terms being added. This time we simply have a 5 and a height of 15. So already if you take a look at these two triangles, the blue one only has variables, but the red one gives us numbers. And the importance behind realizing this before I even get to the proportion is just look at look at the 5 versus the 15. Clearly the 5 is 3 times smaller than the 15. Now if the blue triangle is similar to it, what you'll find is that means R and H have the exact same relationship. H is 3 times bigger than R. Now, again, the easy way to really set this up is simply use a proportion. So, again, there's a couple ways you can do this. I'll just kind of go with the first one I think of, which is R is to H as 5 is to 15. If you wanted to try it out another way, go ahead. It'll always give you the same result as long as you stay consistent. So when we cross multiply, R times 15 is going to be equal to 5 times H. That gives us pretty simply 15R is equal to 5H. Now, what I was mentioning before about what you should observe from situations like this brilliantly shows up exactly as we solve it here. If we divide both sides by 3, you get 3R is equal to H, which just goes to show that the height, or H in this case, is 3 times the size of R. Again, if it's preferable to you to solve for the other variable, you can easily do that here. R is 1/3 H, which again is showing us the exact same relationship. So dealing with similarity and proportion problems really necessitates this need to see when there's similar triangles involved, and when there are, to create these two separate diagrams so that you can create the proportion in order to get this relationship figured out before you move on. Okay, so let's take a look at some examples now on the next problem. All right, for our first example, example A, this is a common similarity problem that's about shadows. So it's a pretty fun picture to draw, but first read the question and find out for yourself what is constant and what is moving. So a man that's 5 feet tall, he is not going to grow during this problem, is walking away from a streetlight hung 20 feet from the ground, and again, that will not change. But he is moving at a rate of 6 feet per second. They ask how fast is his shadow lengthening. So in order to see this question correctly, first thing you got to do is get a decent picture drawn to see for yourself what's happening here. So here's the ground, and here's our guy here who's walking away from a streetlight that is hung 20 feet in the air. So here's our streetlight, and I will draw a little light bulb there, shining beautiful light. And if you look at what's happening, when the light hits our guy, what ends up happening is a shadow is created based on the angle that that light hit the person. Now, in essence, what happens is you get a shadow that's created that looks a lot like this. That just looks cool. So if you notice, we've just created a diagram, and while a triangle is being formed from the light all the way down to the shadow, because the man is standing somewhere in the middle of all this, there's two triangles being created, hence our similar triangles that we're going to be dealing with. So to label our diagram correctly, just make sure that you get all your constants in there, and that anything that is changing in this question demands a variable. So our guy here is 5 feet tall, and our light is 20 feet high. That cannot change. But what is changing? Well, certainly his shadow is changing, so let's give that a variable. Right here, let's call that S. And now you may see this as being pretty familiar from our work we just did. Now, there is something else that's very important to notice. I would not say the other distance is from the shadow all the way to the light. Instead, I would measure how far is the man from the light. Because as he starts to walk away from the light, that is a distance that's changing. So make sure you realize, in this problem here, X will represent how far away the man is from the street light. S would represent how big the shadow is. It's important to think of these variables as you see problems like this. So, as we've done before, you will want to imagine where these two triangles are. And here's that blue one, and here's the red one that surrounds it. And this will be exactly the same as what we had just looked at a moment ago. So when we're dealing with our proportions and our similarity, our blue triangle here will have a side of 5 and then a bottom side of S, and then our red triangle will have 20 and then an X plus S. And remember, the key idea is make sure you can see both triangles and set up your proportions. So if you don't mind, I'm just going to set up a proportion really quickly here. 5 over S is equal to 20 over X plus S. If we cross multiply, you'll get 20S is equal to 5 times the quantity X plus S. That'll give us 20S is equal to 5X plus 5S. Subtract 5S from both sides, and you will finish with 15S is equal to 5X, or better yet, 3S is equal to X. Again, that should look pretty familiar from what we just did. Now, because this question asks us, how fast is his shadow lengthening? What's important to realize is they're simply asking us for ds dt. Now, we don't have a ds dt in this question because we haven't taken a derivative yet. And if you take a look at the information they gave us, they actually tell us in this problem that the man is walking away from the streetlight at a rate of 6 feet per second. So in this situation, they've given us some information. Specifically, they've told us that dx dt, since x represents how far away the man is from the light, they tell us that that is actually 6. So what could we do with our equation now in order to talk about these rates? Well, of course, we could take a derivative. So in this case here, the equation that we had reached earlier, that is the equation we would want to take the derivative of. And in this case, it's a very simple one. It would be 3 ds dt equals dx dt. And there it is. We know what dx dt is. We're solving for ds dt. And so let's go ahead and solve this question. It'll be a pretty simple answer. 3 times something equals something. So we are solving for ds dt. And we know that dx dt is a positive 6. Since he is slowly walking away from the light, that means x is growing. So, believe it or not, that's actually all we have to do now. And then let's divide by 3 to get our answer. ds dt must be equal to 2. And in this case here, since it's a shadow that we're dealing with and it's a rate, that's going to be what units here? That's going to be feet per second. So let's go ahead and write our units, feet per second. And there it is, everybody. There's our first example of similarity and proportions solved. All right, our second example for similarity and proportions is the dreaded inverted cone problem. This question has come up before on AP tests. It's a very tricky question, so hang in there and let's see if we can solve it together. So It tells us a tank in the shape of an inverted cone is leaking out water at a certain rate. They tell us the radius of the tank is 5 feet and the height of the tank is 15 feet. So remember that picture from a couple slides ago? It had a pair of similar triangles, but really they weren't triangles after all. They were cones, okay? Now when you look at a cone from the side, it does seem like a triangle, which means it follows all the same basic properties of similarity proportions that we've already talked about. Now if this were a tank or a container of water and it told us that the radius of the tank was 5 and the height of the tank, is 15, the idea that is going on in this question is there's also some water in this tank. Now, it could start off full, but eventually it's going to be empty. So what we want to do is we want to try to draw what the level of water would look like at some random point in time. Now, here's the beauty about an inverted cone. The water in the tank is like another cone, and it's similar to the shape of the original tank that we had. So if you're imagining this cone right here of water, let me actually just kind of give you a little bit of a highlighted view of what the water looks like, and it's slowly dripping out. The water in the cone, in the container, is its own cone, and the shape of it is similar to the shape of the original tank. So basically, when I set this variable right here r and this variable right here h, right? It's a smaller amount than the original tank, but it's similar in size. So what I want to do right away is set up that proportion that we talked about earlier that helps us relate what r and h are all about. So again, if you recall, here's the smaller cone, really is what it is. I'm not going to label everything too detailed. That's our radius and height, and here's the bigger cone with 5 and 15. So if you recall from what we did earlier, the basic idea is we can say r is to h as 5 is to 15. Cross multiplying, you get 15r is equal to 5h, and simplify that, and you will get this great equation that says 3r is equal to h. Now remember this. It's not just some random equation we're getting. It's telling us that if you triple the radius, you get the height. Or in reverse, if you take a third of the height, you'll get the radius. And this is true no matter what level the water is, because the cone shape that the water is making will always follow this property, that 3 times the radius is equal to the height. So, if you read this question now, they tell us some pretty key information. They tell us, for example, that water is leaking out at a constant rate of 2 cubic feet per minute. Now, that's not radius, and that's not height either. Cubic feet is a volume unit. So what does that mean? It means that dV dt is going to be equal to, and if it's leaking out, we want to make sure we say -2 and cubic feet per minute, if you want to write the units down. Now, again, they told us the base of the tank and the height of the tank is 5 and 15, but the only purpose that serves for us was to figure out, again, this proportion down here that told us what shape the water must always be in. So, what do we do? Well, since the problem involves volume, we know that we have to have the volume equation. So now this is kind of like back to Module 2, where you need to know how to take derivatives of certain geometric formulas. Now for a cone, the formula is 1/3 pi r squared h. Now, if you're thinking, let's take the derivative, here's what I want to warn you about. If you were to take the derivative now, you would get dv dt, which is fine, but on the right-hand side, you would get a lot of variables. You would get some r's, some h's, you would also get a dr dt and a dh dt, and for this kind of problem, that is just not going to work. And so here's the idea. The reason why this was so important to get this relationship right here is so that when the time came, we could come up with an equation for volume that doesn't have v, r, and h. Instead, let's replace one of them so that we can solve for the other. So in this case here, I'm going to take the volume equation that we had, and I'm going to adjust it. I'm going to replace either the radius or the height with something in terms of the other one. Now, in this case here, I would much rather leave the radius squared and replace height, simply because I don't want to have to plug in something into r and then have to square it and deal with all the mess that creates. Now, if you take a look, we already know what h is, and it's equal to 3r. How wonderful is that we get to replace h with 3r in this case. So what happens? Well, the 3 cancels out with that 3, and we're left with the volume equation of pi r cubed now. Now, I know this is not the equation for the volume of a cone, but for this specific cone, it is, because we already established what the relationship was between radius and height. So now let's take our derivative and see where that leads us. The derivative with respect to time of all that will give us dv dt equals 3 pi r squared, dr dt. You don't need those parentheses yet. And so now, of course, we're going to kind of go to our usual method of solving a related rate question, which is let's plug in as much information as we can and solve for anything that might be missing. So let's go back to the top, and first off, we definitely know dv dt is -2, so let's get that in right away. -2 is our rate of volume. Now, we also need to know what our radius and our rate of radius would be. And so, if you read the question here, they ask for at what rate is the radius of the water in the tank shrinking? So we need to figure out what is dr dt. And we should be expecting a negative number since it said shrinking. So down here, we've got our dr dt. So now comes the tricky part. We need to figure out the radius still, but they've only given us this information. They told us that the height of the water is 9 feet. I wish they had told us the radius, but of course they didn't. So if you're given the height is 9, what could we do to figure out the radius knowing that the height is 9? What type of information do we have that could tell us how radius and height are related to each other? Well, once again, see that key formula we had from earlier? Once again, it's going to show its worth now. So if we know that the height is 9, the question is, what is the radius then when the height is 9? And that should be pretty easy to figure out. Divide both sides by 3, and you will get that r is equal to 3 when the height is 9. Do you remember earlier when I said how this container tells us something very important, that the radius is always a third of the height? When they told us that the height is 9, what's great is that means we know the radius is 3. So let's fill in the 3 for our radius, and now we have everything we need. Let's solve this thing. So we'll get -2 equals 3 squared is 9, but times another 3 is 27 pi. And if we want to solve for dr dt, we simply divide both sides by that 27 pi, and we will get dr dt equals -2 over 27 pi. And since this is a radius, we're going to deal with centimeters per second. I believe seconds was the time. Oh, sorry. It was feet per minute. Never mind. So fix that right here. It's not erasing. So cool. Feet per minute. And there is our answer to part A. So we can actually answer the question. We would want to say the radius is shrinking, which should make sense since the water level is dropping, at a rate of, and since we already said shrinking, we don't need that negative sign. So we could say 2 over 27 pi feet per minute. Okay, so now let's take a look at part B. Okay, for part B of this problem, it asks us how fast is the height of the water changing, which simply means that all we have to worry about is figuring out what dh dt is equal to. Now, this is surprisingly easy when they told us already that the height of the water is 9, because that means this is the same situation as from part A. So remember that equation that we had from earlier, the one we've used quite a bit now? it went 3r is equal to h. Again, this was useful for many, many reasons, but now this is the best part. To find the rate at which the height is changing simply means to take the derivative here, and that would give us 3 dr dt equals dh dt. So 3 times dr dt is going to be equal to dh dt. And what was our answer from part A? Well, we already got that from earlier, and that would have been negative 2 over 27 pi. So in this case here, our height is actually pretty easy to solve for now. dh dt is going to be equal to negative 6 over 27 pi, which simplifies to negative 2 over 9 pi. So again, the question asks us how fast is the height of the water falling, so we can again conclude here that the height of the water is falling at a rate of 2 over 9 pi feet per minute. So that concludes the inverted cone problem. Hope you enjoyed it.